Alright, so today is day 12. I'm gonna show exactly what I did today. This week it has been a bit busy, so I have not been able to work as much as I want. For example, yesterday was just 1 hour, and today was around 2 hours. I have like between 6 and 8 hours per day in school, so squeezing that extra time is quite difficult. And yeah, so today we implemented attention from scratch. We are using Tiny Shakespeare, that's a dataset, which is this one. And yeah, it's like the recopilation of Shakespeare. And if we create a model that for that takes as input some character and outputs tries to output the probability of the next one, we are essentially creating a transformer. I mean, we need to outline the architecture, but it will in essence be able to generate more text similar than this. That's the intuition. And the type of transformer we already implemented, it's decoder only. So what we did was the same as always. We reuse this part of the code from previous projects, and we actually re-implemented the bigram. So we're predicting for a given character, we are predicting the next one based on the previous one, and that's it. So we can see that the output is quite bad. And then we also observe how exactly does attention works directly in the matrices. So we have three major matrices, which is the query, the keys, and the values. And what we do is first compute like a weighted average, like a weighted aggregation. And a way of doing it is just like with for loops, but there is a mathematical trick, which is making it the multiplication with triangular matrix. So we can mask also the matrix because we're gonna compute matrix multiplication and it's aggregating like some percentage of it. We're gonna use softmax. So what we do is mask with minus infinity in order for the probabilities to get because e to the minus infinity is gonna be 0 and e to the other probabilities when divided is gonna be normalized. So yeah, it's completely okay. So this is our mathematical trick in order to aggregate and compute all relatedness, like all information sharing in an efficient way through matrix multiplication. So the essence is you have to take the query matrix, multiply it by the transpose of the key matrix, which is this one. Yeah, so this is what I said. We have the triangular matrix. We mask the zeros as infinities, minus infinity. We apply softmax. Then we're gonna have like a normalized matrix with the upper triangular as minus infinity, and yeah, and we have three linear layers, which are basically the key, query, and value matrix. We multiply the Q times the K transpose, and we multiply this by the previous matrix I said, and this is the way of sharing the information. And we multiply this by value, and there is another trick because we need to multiply by or divide over a number in order to make it more because if the number is very big, when you apply softmax, the result tends to be polarized, like into a single value. So if you have a vector and all the values are very large, the resulting vector is going to be like one hot encoding. So the probabilities are going to be around 0 and just 1 is going to be sharing the information. So that's why it's important to normalize this output. And yeah, there is in the paper, in the attention is all you need. Attention is all you need. Attention is all you need. Yeah, in the paper, here, I mean, we can see directly in the image. This is the architecture we are implementing. and for the architecture, we are all implementing this right part, and as we can see, this is what I explained is just one head. What we do is concatenate this in order to have multi-head, and then we have to apply it, the layer norm, which is very similar to batch norm, but it's instead of doing normalization in the columns, we do it against the rows, and we make a final adjustment to the architecture, which is instead of applying layer norm at the output, as we can see here, we do it before the transformation in order to have it's like a better control of the gradients. And I mean, that's it. This is the code in general, and not many, it's not a big code, not many parameters. I ran it without GPU, and we can have now this output, which is not the best, but it's quite a good beginning for a transformer. And that's it.